Good afternoon, ladies and gentlemen. I hope you can all hear me today. My name is Tommy White and I am one of the developers of the MasterSeries. Today we're looking at our connection design software. What I thought I'd do first of all is just to take you through where our connection design software lies in the whole range. So we have a system called the Building Designer Suite, and it allows you to import models from Tekla, Revit, DXF, and put that into our 3D modeling system to do all analysis, and we can exchange files back and forwards through that. That system can then also, that's called our Building Design Suite, that's the core part. We can then integrate our design into all of these different design areas: steel, composite, concrete, timber, connections, and even do dynamic analysis and design. And we can also output RC details and DX files. But today we're just looking at that one component, the connection design. We will be looking at the two different programs, the moment connections and the simple connections. They're two separate programs that run together. And we'll be looking at the system both as a standalone module. I know some of our clients just use the connections for doing that on a daily basis without having the rest of the frame analysis. But we'll also then look at how it integrates directly with our Building Design Suite, with our master frame and our master port. The connections we can do, very simply, I'm just going to run through this quickly, is our eaves, apex and base plates. We can also do beam, column and hollow section splices. Those are all bolted splice connections. In the simple connections, it's a lot clearer. We do beam to beam for flexible fin plates and angle cleats. And we also do beam to column flexible fin plates and angle cleats. And for those who only have the simple connections, we add in a reduced version of our base plate program just for doing axial concentric loaded bases. The reason for that is it's part of the simple connections green book. So the types of connections is very varied. So for eaves connection, we're talking about portals, we're talking about wind braces, and we're talking about valley bays. We're talking about all different configurations, apexes and portals, and as a splice connection. Base plates, we're looking at slab and stiffened, and we're looking at eye sections and hollow sections. And then we come to the beam splices, very straightforward, internal and external plates, column splices and hollow section splices, very straightforward. And then this simple connections are beam to beam connections for our flexibles, our fin plates and our angle cleats. And then again the same for our beam to column splices. Design codes. You get the EuroCode design as we described in the webinar invitation, and it will design to the SCI publication 358 and 398 for moment and simple, or simple and moment connections. And we apply that to the national annex of the EuroCode. Built into the system is the Euro norm plus the UK values. You can then add your own values in if you wish to do design for France or Ireland or anywhere in the world. We also have the BS, so you're not being stranded with this brand new system. You can revert back to the BS, which designs the old system, the old publications, and you can quickly switch between design codes or even annexes to see the differences and national annex applies. So what does all this give you? Very simply, it's a very quick design process. It gives you economical design and gives you a flexible design. So without any further talk, I am just going to go straight in and open up the program and show you how simple it is to use the software initially in this standalone mode. So, MasterSeries 2015 from the 18th of June, and here we can see a confirmation. It is licensed to myself and it is the 18th of June version on a 64-bit machine. So standalone element design, we go straight into connections. And I'll see a list of simple connections files. And what I'll do is I'll pull in one I was looking at earlier from the recent list and get this. So this is our traditional portal frame with a haunch and what we call a Morris stiffener and a end of haunch stiffener. Now the screen is split into three areas. You have the results, you have your graphics here, and then over here you have your input screen. And I'll talk a little bit about this screen in a moment. But let's just look through some of the typical joints that we saw in simpler mode earlier on. So your apex, your base plates with your effective area methods, and your stiffened base plates, and then your beam splices, column splices, hollow section splices, your simple beam to beam, flexible fin, and now the cleats, and then there you have the same for the columns. So that was just a few joint examples. So what I'm now going to do is I'm going to use the program, and I'm going to come back out again and start a brand new file and say element design connections, and I'm going to go for a new file and call it demo 1 and create new. And it's going to ask me for the default information. I'm just going to accept all this, and I'm going to choose a moment connection, a beam to column, flange or eaves connection as we call it, and we say yes. And then it comes with the default setup for me. So first thing we want to do is say yes, its title is eaves joint. We'll call it eaves joint 1, and we're going to look at the forces, and we're going to put a moment in of 450. I'm going to put a shear in of 175, and we're going to put an axial in of 200. And the end of the haunch moment I will put in, and we'll see why in a minute, of 200. The column forces, we don't need to put these in. It'll take them from the initial forces and reapply them. So the shear will become the axial will become the shear. Obviously, once we start rotating this section, it will be resolved. So what we're seeing here is as we move down through the system, we're opening up different windows or zones of editing. We can expand any zone by clicking on the normal expansion. So this is standard Windows interface. We can close them so that we only have the current one open. We can also ask it to collapse everything. We can ask it to only show me the column information. So I'm looking just at the column data, or I can look just at the beam data. So I could even say let's expand all, and it's giving me all my input data all in one go, so that I don't have to keep expanding and closing. My preferred method, if I just collapse all, is to go and use the expand only the selected category. And to use that, we just click on the title. We don't click on the wee arrow, we click on the title. And we come in. So let's set up the column. I'm going to change that. So click on that. I'm going to change the grade to 355. I'm going to click on the beam properties so the column properties collapse. I'm going to accept that. I'm going to put in a 6-degree slope. And once I'm in here, I can just cursor down and type in the value. So I can say the haunch length is 2100. Cursor down. I don't need to use the mouse all the time. I can happily work in here if I want in a faster keyboard method. Haunch depth, I'm going to say 900. Okay, bolts, grade 8.8. If I wanted to change those, I can click inside and expand that and come in here and then choose the value. But I don't even have to, because if I come back to my bolts, I can just come in here, sorry, and just type in 10.9, and it will know that that refers to the bolts, not their diameter. And I just change that back to 8.8, so I can directly overtype information and it will intelligently use that information. So we have our bolts at 90 centers, I'll leave them at that. Bolt rows. I've set up the information so that we automatically have 3 rows of bolts. So we're now into the area of where we actually now need to do the actual design. So we've set our basic forces, we've set our basic geometry. Now we need to put enough bolts and stiffeners in. So looking at the results, we can see 2 things. There's a failure over here on the left, which is the actual capacity of the section. So we have a failure of the joint of 48%. But on the right, we also have a blue background, which tells us that something is clashing with something else. And this little shaded area tells me also what it is. And if I just go to DIMS, it will just tell me that there's a problem with the bolt accessibility. It can't or may not be able to fit that bolt in. So it will be wise in the lower bolts to come along and make that 120. That's now working, hasn't affected the capacity, so I now need to come along and add another row of bolts in, and I'm going to make that at 90. And now my failing is the compression stiffener. So straight to main stiffeners, bottom stiffener, and I'm just going to say put me in a 10mm stiffener. And now the joint sort of works. There's one more failure left to solve, and that is, in this case, you will find to the EuroCode you're requiring to put in end stiffeners and haunches more frequently. So the web bearing is not very happy. So coming back, I will come back to the main stiffeners, to the end of haunch stiffener, and I will put a 10mm stiffener in there. And now my connection is white. It works. So what do I want to do next? I want to make it have another loading case. So I was doing the general loading case Dead Plus Live. I'm going to add in a case, and I'm going to put it in as Dead Plus Wind Uplift. I hope I can spell, and I will elect to print this case. So yes. And now the beam forces. Moment is going to be negative minus 275. Shear will be negative minus 125, and the axial will be negative minus 75. End of haunch moment again. If we don't put anything in here, it will use the lesser of the capacity of the section or the overall moment applied. So we don't need to affect our properties, we need to put a stiffener in here. So all we need to do is come back down to main stiffeners and put in a top stiffener. And I can just say 10. And it understands that I'm putting in a 10. So 10 has given me an improvement, but I now have a problem with welds and I need more bolts still. So I'm going to put another row of bolts in there, which will also hopefully relieve the weld. So bolt rows. And you'll notice I have 4 rows of bolts, I just haven't used them all. And that's a little trick that's available in the program, whereby once you've got a basic configuration, you can actually save that as the template for any new eaves joints. So I had set up 4 rows of bolts top and bottom with only the first row activated, just to save me time and make it more intelligent. So now with that extra row of bolts, it's lightened the load on the weld, and we now have the connection that works. But what about the first case? Let's just check the first case, and it now is a problem. So say we hadn't looked at that and we thought, oh, things are fine, I put my second case in. We do have a little trick up our sleeves. We can actually scan a joint and it'll look at all the cases. If you have 5, 10 or 15 cases, it'll scan them all and stop where it finds a failure. So now we have a slight problem in the column tension stiffener. And I suspect it's a welding problem. The weld. it needs a slightly larger weld. The welds, the 1/√2 welds, aren't always good enough. So that is a main stiffener, and I'm going to put in top stiffener, and I'm going to put in an 8mm weld, and it now is happy. And just to make sure nothing has happened wrong, it's okay. So that's my first joint done. 20 minutes, but then again 5 or 10 of that was talking about the basic program. I want to add in another joint, and I'm going to go for a base plate this time. And I'm going to take a slab base plate, and I'm going to put the forces in at, I think, around 1100 is what I can take in one of these boys. And if I scroll up, I can see that the connection could resist 1600. So 1100, and I'm then going to put in a very low 10 kilonewton moment, and it is by default all working. Now, one of the tricks is that in the EuroCode you use something called the pad diffusion ratio. And this is a wee bit of training for you, because I know somebody's already asked the question about this. And not in the column properties, but not even in the basic base plate, but in the concrete. We have the concrete grade and the grout grade, and that is the cube strength. And we then have the cast-in depth for pulling out bolts. But what's more important is two things: the concrete depth and the edge distance. Now 1.5 is the normal ratio that you use. But if you know that you've got quite a good edge from the edge of your base plate, technically it will be from the edge of the concrete compression zone, from that point or that point. But just play safe and take it from the edge of any part of the base plate. And I'm going to say that I know I have quite a large base plate, so I'm going to have something around 500 square. So a 1500 square pad, I'm going to end up with 500-600 each side. And that is, as I move down, move that up from 1.5 to a far more enhanced 2.13. So that's a way of getting a far higher compression capacity on the concrete. That pulls the whole compression zone back in again, and therefore allows the maximum thickness to be or cantilever to be 31, so we actually can end up with a thinner plate. So we can actually come down. We are using a 20mm plate, so we cannot get any lower down than 16.3, because we can't go to 15, that would fail. If I put that back to 100, we would see that we actually now need a 19.2. So in some instances, paying attention to this distance will give you an enhanced capacity of your section. So that's a very simple base plate, done in 2 minutes. No stiffeners, no nothing required. I want to add another joint. And we will look at, I think I'm going to look at a column splice. So I'm going to take a column splice. Yep, the forces, ultimate axial is going to be, and I'll just have a quick look at what are the capacities. 1600 and 2300. I'm going to put in the axial load coming in here is 1200. So quite high. And the minimum axial is going to be probably less than half of that, 500. So the minimum axial is used against any moment, and I'm going to put in a moment of, say, 10 kilonewtons. And it calculates all those values, and it says, yes, it is acceptable. That's because the whole connection is bearing. There's no net tension, and it's bearing. If I come along and I put in a gap between the two columns of, say, 5mm, it now ends up with problems with the webs, the bolts, and other things. In this case, this is using the standard 3 rows of bolts, so it usually should work unless we're getting into high moments. But where the program really wins is, and I'll look at the web in a moment, is when we start to apply minor axis loads. So we say we also have a 5 kilonewton minor, a 100 kilonewton shear minor. We have LEX and LEY of say 3, no, let's make it 3, comma 3. And we've now taken them 3 meters long. We now have internal moments being calculated, and we end up with a maximum internal moment of 24, not the original 5 we'd applied. And we now just need to start designing this in more detail. We do find that the strut action moment is causing us a little bit of a problem in that we're overstressing. So my imaginary joint is probably, to have minor axis loads, is probably having too high an axial load. So pull that down to 1000, and that's now happy. We're not overstressing locally in the material, but what we do have is the web and the minor axis flange capacity to sort out. So let's look at the web first. Always look at what the results are showing you. Don't just go and click on buttons and hope it works. So what is failing is the shear load of the bolts. So we probably need to see what's the limit. The bearing is 79 and 67. So those are the bolt shear capacity is okay. It's the resultant bolt capacity against the applied loads. So what I need to do in the web is look at maybe going to 10mm plates, see if that solves it. No. And my other guess would be to add another row of bolts, so make that 1. I'm just going to push the bolts up, and I need just to make the half length now a bit longer at 150. Oh, sorry, I forgot a 0, 150. And now that's all working at that. I could tidy that distance up if I wanted to, but I'll just go on and look at the minor axis flange. So minor axis flange, it's the combined unity. So the minor plus the major axis is giving us a ratio of 1.4. So we do really need to increase the flange thicknesses. And that's pretty straightforward. Cover plates, and interior, exterior. And I'm going to go, well, it's 1.48. I reckon 15mm should cover that just nicely. And there it's done. So that is now my solution with my little packer plates of my section. And just so that I can see this a bit clearer, just zoom in, and then we'll see all the information written here. Now, we don't have to use this style of layout. We can go for the old-fashioned layout with the connection graphics over here and a small results button. The modern widescreens, the default now is for the full height results. So let's look at a simple connection just before we move on to integrated design. And I'm going to go for a simple connection. It's going to be a flexible beam to beam. And we'll see immediately that it gives us a connection that looks right. So if I come along and I say, right, my left beam is going to have a shear of 350, it's okay. And if I go and I say my right section, and I'm going to change the section this time. Sorry, double click on the section and change the section in the drop list. I'm going to drop this down in size to be 407. So we now have a little problem in that we need to be careful of these bolts. This bolt could be clashing with this bottom flange. We got two choices. We could take this bolt out of this side, or we could just leave an instruction to strip that flange back. In my case, I need to put my shear load in here. 300 is too high for the right hand beam. I'm only guessing. I'm going to make it say 200. That's okay. So all we need to do is to make sure that we can get away with 4 bolts each side. So back to the left plate, and if I just tell it that there are 4 rows of bolts, it'll automatically cut back the plate to suit. And that is my joint designed for you. So very simple to do it. Now one of the things you'll notice, and it's not that critical in these bigger beams, is that we have the default 50mm notch. But a lot of people don't like them, particularly when you're in the smaller section sizes, because 50mm out of a 203 or a 305 is quite a lot. So if I go down and put that in as 1mm, it will tell me that it needs 28. And I, in this case, would just say make it a 30 notch. And that's it done. Very straightforward, very, very easy to do. And just repeat the same process for a column, but this time on a column I'm going to choose a fin plate. And I'm going to say OK. And I'm going to come down this time. And in something like the fin plate or the columns, it's very useful to use the filters, because when you filter, you only see that component of the design as well. So let's look at the beams coming into the web. So the web beams, we're going to have around about a 400 shear. That doesn't look too happy. Make that 300. So it's happy, but there's something unhappy. And I come down to the right section, and I'm going to make that into a different section size. So I'm going to change that. I'm going to make that right up to something quite broad, just for the fun of it, and you'll see why in a moment. And if I then come along and put its section loading in as say 500, we get some failures. And we're actually going to get the failures on the supporting member because the column can't carry the resistance. So even that, we are probably down to about 300. And we've got a little problem in the supporting member. So we'll have a wee look at that. But before we go, we don't want any sections. So we can just go straight to the top and say flange section, no. And here, flange section, no. And we now are back to our simpler joint, and if we ask to draw everything, we will see that we only get those details. And I'm just going to move that a wee bit over there out of the way. So our section with our member supporting, let's see what the problem is of 12%. It's the combined shear on the column web. That's what I thought it would be. So it's this web of this supporting section. And 254.73. And obviously you might decide to go for a heavier section. Another solution would be if we had the room to make a longer plate. I don't know that I can get enough length in there without having to strip things out. So in this case, it might have been a better solution to use a flexible end plate. In my case, I'm going to have to play humble and go back and reduce that section loading down, say 250, so that it works. Obviously, the other alternative, and I forgot about that, would have been nowadays, quite frequently, engineers design in 275, but it is not a cost prohibitive to actually use the 355 grade of steel, particularly something like a 254-73 UC, which is probably going to be a stock item, being the lightest of the 254s. So as a fabricator, you could make that decision to do a substitution as long as you know to put it in properly. So that's a quick run through of the connections in standalone mode. You get all this lovely output. And what does the output look like? Well, it is what you see here. is the simple answer. And I can print that to a printer. So I'm going to print all of my joints, all 5 of them, full output. I'm going to take a full page for the graphics, and I'm going to put all the selected cases, and I'm going to print it to a PDF writer called PDF Creator. So there's your joint, and I left it on landscape instead of portrait, and that's why we've got so many pages. And there's your next joint. We'll do it the right way around for the next output, and it's actually now managed to flick itself because it says no, it makes more sense. I'm giving you the results the right way around. So I accidentally had sent it out landscape initially rather than portrait. Now, we don't have to print everything, because I go back to print, I can go and I can say print graphics and summary only, and I'm going to take all joints. So a lot smaller. This should work. If not, I'll get one of the developers to look at it. And print. And 6 pages. That's sounding very promising this time. That's probably only the beam to column splice that need, or beam to column simple connection that will need 2 pages for its output. Yes, replacing it very quickly. Over it comes, and this time we have them all 1 per page, except for the one that took 2 pages. So very simple. You can have detailed or reduced output. You can also, if you are a PowerPad user or a Office Tools user, export that to Word. And I've asked it to export just this one joint to Word, and I mustn't have turned on the newer version of the printing routine, which is a lot quicker. Now we're finished. Thank you. Goodbye. Right. If I go back to, say, the eaves joint, that's not too bad. That's pretty straightforward. If I come along to a column splice or even a beam splice, so if I actually take a beam splice, a new beam splice, there's no reason in the beam properties that I can't come in and say this 457. So I can say that I can have a 457 that has a cell depth of 600, and suddenly the whole beam is 600. Or, so if you're doing a cellular beam, you can put in the cell depth and get that designed. Or we can come in and do something even more fun, in that we can choose not to use a UB or a UC or any of the European sections or American sections. We can use a built-up section. So we can start and we can create our section. So here we go. We can use an ASB, or we can start and stipulate the value. So I can say I have a 600 section that is got a web that is 15 thick, and watch the thickness of the web. No, not 1015. And that's got thicker. The top flange I'm going to make, that will be fine, and the bottom flange I will make 250, so we can have an asymmetrical section, and the bottom flange I will make 20 thick. So we'll have a thicker asymmetrical section. And so we can have, instead of a cell form, we can have our own built-up section defined. So we can not just do the European and British sections, we can do the European, the British, the American and the Chinese and South African section groups, and we can do built-up sections and cell form beams. So very, very straightforward too. We mentioned at the very, very start that we work to the EuroCode to the UK National Annex. We can create our own or use the standard values. In this case, it doesn't actually make a difference. So we're now using the default values from the EuroCode, or my case, the UK values, and it tells me that. If I want to have a quick comparison between two designs, and let's go back, say, to my eaves joint. Would that work to the BS? Now, bear in mind that the load factors are different. Well, I can either choose it from here and say BS, or I can just click on BS. So back to BS and to the British standard. With those lighter loads, obviously it would work. And as we see, everything below about 90%, we're not too worried about it. Haunch welds are just ratio, so we don't worry about that. So we can at any stage flick between the two. Now, the one last thing is we can send this data straight out into an AutoCAD drawing. And I'm going to stay at 1, and I'm just going to spread these out a wee bit so they're not too cramped. And I'm going to be happy at that, and I'm just going to say export to AutoCAD at 1 to 15. It's going to open up an AutoCAD drawing and bring in my little details already drawn. And there I go with my joints all placed all around the place, and everything is on lovely layers. If I go home and look at my layers, I can see that I can ask for different layers to be turned off. My joints layers, so I have joints, bolt center lines. So if I wanted to take out the bolt center lines, they've now disappeared. I'm back in again. So we have a full access to sending our data straight out to AutoCAD as well. So we'll just not save that, no. Okay, now, I did say that other way of using the software is through linking to MasterFrame, the building design suite, which is MasterFrame, or MasterPort. So I've set up myself a little oddball frame that's sort of half portal, half multi-story. Loads don't really make much sense. It's more to the section sizes just to show you how it works. So going into design, rather than steel design, we go into connections. Very straightforward. It's fully integrated. And I say, yep, I'm going to use those defaults again, and I want to do a eaves connection. And it's asking me where, and I'm going to pick, say, that rafter. And it's pulled the data through, pulled the slope, pulled the section sizes, pulled everything, and we can see it's failing. It's failing quite hard. So first thing is get this away from in blue, and like before, we need to lift that bolt up. So very simply, bolt rows, and I'm going to change that to be 120. So now we need to make this a bit stronger, and this could be fun. We may not have a solution that works, but let us try. Main stiffeners, bottom stiffener. I'm going to put in a 12mm stiffener. So now we're down to 71%. So 2 more rows of bolts should do it. I'm going to say 90, 90, and it's now working. In this case, we have all these different loading cases, including horizontal, notional loads, and everything come through from our frame analysis, and we can just scan all the cases. It's running through the different cases and checking there's no problems. We can do a quick base plate, add in a base plate, and I'm going to choose that column there, and we'll see the compression zone is a wee bit of a problem. Check our concrete, that looks good. Edge distance, I'm going to say yes, I'm going to have at least 400 all around and a 450 deep pad. I just need now to take my base plate and make it bigger. So it's 220 wide, I'm going to make it 250. And it is 470, I'm going to make it 500. Doesn't sound like a lot, but all we need is to get this equal distant projection, and now that joint works. Does it work for all loading cases? Very good question. Let's scan that, and it's now running through, and we're happy. Very, very quick and efficient design. Even if you have the connections but not the frame analysis, you can actually get the frame analysis file and the results file and use that to interrogate your design so you can speed up your own design process. So that is the main crux of using the software. That is the whole essence of using our connections programs, 2 programs as I said. Now, if you're not a user, you're welcome to request a 30-day trial on the software. And all I would do is I would go to the connections website page. So from home, go to product range, steel design, and from steel design to connections. And in there you can say, I want a trial. And it will ask you, so I'm interested in a free trial, pop in your details, and it'll either go to us or to one of our distributors. So if you're using the software out in Nigeria, for example, if I can spell, that's N with an I. That will be going to computer design systems in Nigeria rather than direct to us. So you'll go to your nearest reseller. So questions, do we have any questions that are needing to be answered there, Martin? Let me have a look. When multiple cases, can the program identify the worst case? Actually, that's a very good point. It's something I didn't actually show you in the program, in that I could have actually asked the program to design the joint either standalone or integrated using its own parameters, so 90 centers, 10 mil thick, and just say go. And it's going to try and find a solution that works. It actually found with a slightly better spacing, it works with only 2 bolts up there. It's smarter than me, and it's not increased that because it's saying, well, it's so close to the edge, you should be able to get the bolt in. Do you want to move it up or not? So AutoDesign is available to you to do that. And the most important thing about AutoDesign is it then selects the loading cases that are critical. So it sets the most critical positive and most critical negative moment cases to be printed. In the old version of the connections, you could only print 2 cases or everything. In this version, you can select on a case-by-case basis. You will see that hopefully this one is set to no because the notional horizontal force, case 4 is more critical. And I assume I have a reversal case. Maybe I don't. That's giving me a negative moment. There we go. Case 47 is the most critical in reversal with dead plus wind. So yes, it will select the cases for you after an auto design. And the other nice thing is in the auto design that people miss is if you've set up your joint but just want to check, if you lock the design, it'll never take anything away. If it finds a failure, it may add another row of bolts, but it won't take anything away. So it will start there from scratch. So it starts from that and doesn't remove anything. How do you set 4 rows of bolts as default? Okay, this one has 3. I'm going to add in 4, and I'm going to add in 5. So I've now got 5 rows of bolts, and I've got a hunch, and I've got some weird loads, and I can now just go to utilities, use this as my default. Any questions at all on the software, give me a shout. My email address is very simple. It's Tommy, T-O-M-M-Y, at MasterSeries.com. If you're unsure where to find that, just go into the contact and just email help or sales. Sales will get me more directly. Okay? And again, if you want to try the software, again, just come in and request a trial of the software at any time. So it just takes me to say thank you very, very much for coming along today. All the best.